Okay, guys, so let's continue our uh, discussion on deflection. So again, we have finished the concepts on immediate deflections, which are more focused on those elastic deflections that exist immediately upon the loads are actually applied. Okay, so for the long-term deflection, this is actually a very difficult thing to calculate in the sense that it's a mixture of two or three influencing factors like temperature, humidity, and sustained loadings. Okay, which is brought about by what you call the secondary deflection due to shrinkage and creep. Okay, so when we are talking of temperature and humidity, okay, temperature and the moisture or humidity, we are actually concerned on shrinkage deflection. Okay, so this shrinkage deflection is actually affected by the presence of humidity and the influence of temperature, while that for sustained loadings, we this is actually uh, causing your beam to deflect in terms of what you call a creep. Okay, so creep is something that happens when the loads are sustained uh, all on the beam or the slab for a long period of time. Okay, so both of these actually are time-based parameters or variable because they are affected uh, without without any external influencing load. The deflections are actually increasing or maybe increasing due to the temperature, humidity, sustained loads in a considerable amount of period of time. Okay, so the formula is actually simpler in ACI than proposed by a lot of authors in the book, and this is a practical way of handling your long-term deflection because, as we all know, the prediction for deflection is quite very difficult. So what ACI did is just to come up with this simple equation to let us have a feel on what to expect on the computation of this long-term deflection. It's given by the formula lambda delta multiplied by delta sustained. And what is delta sustained here? Okay, so we have actually a lot of delta to consider. We have the delta dead load, the delta live load, and the delta sustained. Okay, so the delta dead load and the delta live load are simply due, of course, to the dead load effect and the live load effect. But what is a delta sustained? So a delta sustained, the word sustained here simply refers to those loads which are permanent, like the dead load plus a portion of the live load. Okay, so this is sometimes assumed to be zero if your condition for such structure is just ordinary. Okay, but when you are uh, dealing with structures such as warehouse and storages and garage, no, this can actually increase up to 25%. Okay, so from 0% on ordinary condition to 25% on garage, storage, and warehouse. Okay, so these are the sustained loads. But at times when this percent live load is zero, then this is just the same as delta dead load if percent live load is 0. Okay, so that is the way on how to understand easier what is sustained, what is live load, what is dead load. So for delta LT, which is the long-term deflection, we have to simply multiply delta sustained with that of a factor lambda delta, where lambda delta is simply a formula to handle what the creep and the shrinkage effect. Although in the ACI, the formula for lambda delta is actually very focused on primarily on creep shrinkage. Okay, or sorry, on creep primarily on creep deflection. Okay, although some authors tells us that the consideration for shrinkage is already there, but still, if you look into the formula, it's all about the Kasi factor, which is brought about by the graph here that is shown. Okay, so wherein the Kasi factor is the time-dependent factor for sustained loads, which can show you that this is purely almost uh, a consideration of your creep influence, okay, or your creep factor. And of course, rho prime is a compression reinforcement which affects your creep deflection, such that your formula there is actually a function of your compression reinforcement ratio. The tension reinforcement ratio will no longer affect the long-term deflection, because the modulus of elasticity considered and the moment of inertia considered has already uh, have a part in terms of the tension reinforcement. Okay, so for the figure here, the multiplier Kasi for as the time-dependent factor for creep is also given in terms of uh, of a table here, but still you need to roughly make some interpolations in order to get a more precise value in between. Okay, so you can interpolate it if it is between 5 to 12 months, so it will be between 1.4 to 2. You just make use of a ratio and proportion to deal with it. Okay, so let's look into the procedure on how to check deflection in beams. In general, we have 4 cases, as I have mentioned a while ago in the table 9.5b, wherein the two conditions are actually the major consideration. One is those which are not supporting any elements likely to be damaged, and those which are supporting elements likely to be damaged by large deflection. So in all cases, we simply need to compute for the deflection caused by the immediate live loads. And then for case 3 and 4, we have to add up to the effect of creep and shrinkage, in which the ACI actually simplified it in terms of the formula lambda delta times delta sustained. Okay, so here are now the steps involved on how to deal with the computation of your uh, uh, deflection control procedure. Okay, so first we have to compute for the crack and the uncrack properties at support location and at the midspan. So take note that the direction of bending or curvature including sectional geometries and reinforcement may not be the same. Okay, so take a look that what is meant here is we need to have a crack and uncrack properties. Okay, at support location and at the midspan. So for the uncracked properties, sometimes we only deal with the gross. Okay, so this can be represented by the gross properties. But if you want to make a more precise solution, you can do an uncracked property solution, which is a little bit difficult, especially when you consider a T-beam. Okay, so take note that we have to be cautious on the bending curvature, because if we have here a beam, okay, at the support, so my cross section will look like this. Okay, support, and at the midspan my cross section will look like this. Okay, not to mention that your AS here might be different. Okay, so this might be NAS 1, NAS 2, and NAS 3. Of course, the width of the beam all throughout the section may be different. It may be the same, but for T-beams, it will be again different. Now, if this is a T-beam, then you have a T-beam here, but here you have a rectangular beam. Okay, so if this is a T-beam here, so this must be also a T-beam here. Okay, but here you have a rectangular beam. So you have to compute for your I here, IE1, IEM, and IE2. And for IE1, you have to compute for 2, which is the I crack and the IG, okay, or the I uncrack if you want. Okay, here you also have 2, the ICR and the IG or I uncrack. Here you have also 2, we have the ICR and the IG or the I uncrack. Okay, so you have to consider a lot of things when you uh, go about your step 1. For step 2, you have to compute effective moment of inertia under ACI equation 9.7 using the properties and moment ratio at 2 different stages. So the first stage is a dead load or the sustained load stage, and the second is the total stage, the dead plus live load. All loads considered shall be service load since the analysis is a serviceability procedure. So what does this step 2 means? So step 2 means that you have 2 stages. Okay, you have the first stage is you have a dead load stage. Okay, if you also have a sustained stage. Okay, so sustained stage, so this may be equal or not depending on the percentage of live load. So if percent live load is 0, then DL is equal to sustained. Okay, so for the next stage, we have the dead load plus live load stage. Okay, let's make this A and this is B. Okay, and for the third step, we have the third stage, which is the live load stage, equals the dead load plus live load minus the dead load. Okay, so that's how you compute for your stages. We have two stage here and one stage dead. So for the number 3 here, we solve for the immediate deflection considering the two stages. Okay, so the stage 1, this is the formula, and the stage 2 is this the formula. Take note that here, your MTL is simply MDL plus MLL. Okay, so that's the total load stage. Note, percent live load is normally ignored. But if it is not ignored, then your delta sustained will be computed separately. Okay, if percent live load is not equal to 0. So note that IE here, it may not be the same for the two stages. Okay, why? Because we are considering different crack patterns on on sustained load stage or the dead load stage with the total load stage. So they may not be the same. Okay, so reason why, because of different section crack and reinforcement patterns. Okay, now you compute the net deflection. Delta ILL is simply delta ITL minus delta IDL. And for cases 1 and 2, a comparison shall be made using only delta ILL, 1 L over 180 and L over 360. So if the computed value is less than the limit or the allowed value, then the deflection is controlled. So for case 3 and 4, what will be different is we have to add delta LT with delta ILL. Okay, so delta long term must be added to your delta ILL and compare it with this one here. Okay, so I think there is some missing here. So this must be lambda K delta. Okay, so we can rephrase this by delta ILL plus delta sustain. Okay, delta ILL plus delta sustain. Okay, take a note that this is still to be multiplied by lambda delta. And so again, we have to compare it with this is the computed again, versus your limit. So if this is the computed is less than the limits, then case 3 and case 4 is satisfied. Now, do you have to compute all for when the type of the member is not given? You compute 4, no? So when the type of the member is not given, you compute all cases. But if the type of the member is already given, you only compute what type, no? So this is type 1, type 2, type 3, case 3, and case 4. So if your type is given, type 4, you only compute type 4. But in case the type of the member is not given, you have to check for all 4 cases so that your report will be complete, no? As much as the one who is reading the analysis will be uh, well informed regarding the matter. Okay? Okay, so we will be able to understand this better after we solve one example in this. So for now, I hope you understand how deflection is controlled using the ACI procedure, and I'll entertain your questions synchronously after this video. Thank you very much.